Okay. Well, what we're going to look at today is the end behavior and key features of rational functions. So there, we will have a sign-in link in the future, but the school hasn't sent it to me yet, so we won't have one tonight. But I'll have your attendance here. Okay. So first, reminding you about end behavior. When you see end behavior, what that actually means in behavior is that it's talking about what's happening to the function in most cases when we're talking about going off the screen to the left or to the right. So the end behavior would not be what's happening on inside the graph in this area, but rather what's happening as we go off to the right or as we go off to the left. That's what we're talking about. So the end behavior, this would be the right end behavior. And this would be the left end behavior. And I put the hyphen in the wrong spot there in that first one. Yeah, we'd be talking about that hyphen needs to go right there, the right end behavior and the left end behavior. That's kind of what we're looking at to start this lesson off. Okay, but there will be some cases where we don't, where the end behavior doesn't go all the way to the far left or to the far right. There will be some cases where our end behavior might be something like this. Let me switch colors. Where like on a log function, where it does go to the right end forever, but the left does not go left forever. It approaches like an asymptote. And so this is case 2. That would be the left end behavior this time. In case 2, let's call this 2 here, and this would be the right end behavior. Okay, so as you hear me talk, that's what I'm referring to when I say end behavior. Any questions over that so far?
No, I got it.
Okay, perfect. So let's go over some of the basics with it. So we write them as limits. And if you remember with a limit, you can kind of read it as what's happening to y as x approaches whatever the value is. So in this case, it'd be what's happening to y as x approaches the left, or what's happening to y as x is approaching the right. And the number c is just whatever it's going to, whether it's going up to positive infinity, down to negative infinity, or if it's getting flat at some constant. Okay, so let's talk about example 1 here. It says, describe the end behavior of this function. Now I have a question for you, because this has been a long time. This is unit 1 here. Do you remember when you're looking at, this is called a polynomial. What do you look at on a polynomial to determine the end behavior if you're not allowed to graph?
Exponents?
You do. And in particular, do you remember which exponent you look at?
The largest one, 4.
That's right. You look at what's called the highest power, which we call the degree. The degree of the function, which in this case is the 4th power. And we can also just call this a leading term because it will matter if it's positive or negative. So we're going to look at the leading term and the degree. So on this problem, the degree is 4. And the leading term would be 7x to the 4th. Now, so why does that matter? Well, you can estimate the end behavior of the function by, if it's a polynomial, by looking at the leading term and the degree. So if it's an even degree, it's going to end up looking like a parabola. Either both ends are going to go up as we go left and right, or both ends are going to go down. It's going to be one or the other. Since the leading term is a positive greater than 0, this function is going to look like this. Now, it might have all kinds of craziness going on in the middle, but ultimately, it's going to go up to the left and to the right. And so the way we write the end behavior, again, all this is without graphing, is, let me say end behavior here. You would describe the end behavior in this form. You'd say LIM. That means where the function's going. And in particular, we're talking about the y values is going up. So positive infinity as x approaches negative infinity. That means as we go left, the function goes up. That would be that arrow there. And the second limit we could write for the end behavior on the right side is we would say this function also goes up to positive infinity as x approaches the right. And so we'd write the end behavior like that. So after doing one example, do you remember this, or where are you? Like, are you going, hey, I kind of remember it, or got this down?
I could kind of remember it.
Okay, great. That's good to know. So with that being the case, I'm gonna go on to the next one. And so tell me on this one, what do you notice? First off, let me ask this question. Is this one a polynomial?
No.
Actually, it is. So a polynomial is whenever all the terms, it's just a bunch of what we call monomials adding and subtracting together, meaning it's just a term of x raised to a power with some constant in front. So this would be polynomial as well. And so we'd go through the same steps. And don't worry, I'll show you the other functions here in a second. We would go through the same steps. We would identify what's the degree. What would you say the degree is in this problem?
13.
That's right, which is an odd number, which means it's going to look like an S curve. And we would also note what the leading term is. In this case, what's our leading term?
2.
Well, it'd be 2x cubed, 13. You would include the whole term like that. The 2 would be called the leading coefficient. So that is kind of tricky in that regard. Okay, so now if I went to graph this, because it's odd and it's a positive power, 2x to the 13th will look something like that. Now, technically, if I want to be more accurate, I should have made it hit the y-axis at -1 because that's the constant at the very end. If you plugged in a 0 for the x values, everything would cancel out except the -1. So anyways, I made it a little bit more accurate by shifting it down. And then we could write our end behavior again. So that would be the left end. 2 will be the right end. And so we would say for our left end behavior, the limit of f of x. Actually, this one's called g of x. Sorry. Let's erase that. We call this function g of x up in the equation. This one, we go down as we go to the left. So the symbol for going down is -infinity as x goes left, which is also -infinity. And the second end behavior, the right end behavior, is this function goes up towards positive infinity as x increases without bound, or goes to the right without stopping. And that's how we would write our end behavior for the function g. Questions so far?
No.
Okay, so what could happen to get tricky? Well, they could do this. They could mix up the coefficients, and so you need to remember that this would also be a polynomial. And so what you would do this time on this problem is you'd make sure your degree was not just the first term, but the highest powered. What's our degree?
Seven.
Okay, here's 7. There's something that's bigger than 7. Keep looking. Which power is the greatest power?
8.
8. There you go. And so since that's the degree, then the leading term is the term that's attached to it, which is just -x to the 8th. So here's a question for you. Would this be a parabola or S curve this time?
Parabola.
That's right. And because it's negative, it'll be upside down parabola. And again, if I wanted to make it more accurate, I can make sure it hits the y-axis at +4. But that doesn't really matter for end behavior. So now I can describe my two end behaviors. So the left end behavior, you'd write LIM h of x equals, and since it goes down as it goes to the left, we'd say -infinity as x approaches -infinity. That means as we go left, the graph goes downward. And then the right end behavior would look like this. LIM f of x equals, as we go to the right, this graph also goes down. And so that would be our end behavior there. That's how you would describe the end behavior. So that is how we do polynomial functions. You look for the degree and the leading term. Any questions on polynomials?
No.
Okay, well, let's look at some other functions. So polynomials were where we started this school year with Unit 1, specifically the first 7 lessons. But as we moved into Unit 2, we started talking about logs and exponentials. So what do we do with logs? Well, if you remember, logs by rule, a parent function of a log. Let me do this. Actually, I don't think I was putting arrows on the other one, so I'll just stay consistent here. The parent function for a log is that the domain typically is for a log that x can't even be equal to. A logarithm on the inside must be positive. The argument in here must be positive. So typically we'd say x has got to be greater than the zeros. In this case, though, because it's x minus 2, we'd say that x minus 2 has to be greater than 0. And so to solve for the domain, we would just do an opposite. What is the opposite of subtracting by 2?
Adding 2.
That's right. And so x is going to be greater than 2. That means on the graph, this graph will not go to any x value that's less than or equal to 2. So it's going to be on the right side of that vertical asymptote. That's what I just graphed there, x equals 2. And logarithms, if you remember, they're all reals. Because this is a positive logarithm, this logarithm will go up and to the right because it's positive, and it looks like that. So that would be the graph of k of x there. So if I want to do these two end behaviors, this time it'll look slightly different. So the first end behavior, the left end behavior, we would write limit of k of x equals. Now, as we go left, this graph doesn't go left forever. It's approaching that vertical asymptote at 2. But it never actually gets to x equals 2 because the function would be undefined. So the way we represent that is we would say a 2 with a plus. That just means we're on just to the right of 2. Now, as we approach x equals 2, this graph goes downward. It decreases to negative infinity. That would be the left end behavior. Now, if we want to find the right end behavior, I would again write the limit of k of x equals with an x arrow. Now, what happens as our graph goes right? Well, the graph rises to positive infinity, and it's without bound. So we continue to go right forever. So this time we would have infinity, infinity, but as far as the limit of for the left-hand behavior, x would approach 2 from the positive side, meaning the right side of the graph, as it decreases. So I want to point out the differences here. If it's a polynomial, your answers, oh, I got a typo there. I shouldn't have put an F. This problem was H. So let's get this right. If it's a polynomial, you'll always be writing your limits with infinities unless there's a restriction. But if there's no restriction shown, you're going to only use infinities. So there's B now. And here is A. Notice that our limits only contained infinities. But functions like logarithms, because they have a restricted domain, they will not be only infinities. This one, in this case, we had a 2 plus on the x. Question over that?
No.
Okay. Well, I'm going to keep on rock and rolling then. So now let's take a look at an exponential function. Now, if you remember exponential functions, this is exponential here. This is exponential. And you know what? I should put a note on the last one. I don't think I said it. This was logarithmic. Now, exponentials have a domain of all reals, but if you remember, exponentials also have a horizontal asymptote. So the horizontal asymptote is whatever the d value is of the equation. This right here would represent our horizontal asymptote. Well, it'll be y equals that amount. So I'm going to go up on the y-axis 1 unit, like that, and we're going to have a horizontal asymptote. Now, because my a value is less than 1, because this is less than 0, we're going to be on the negative side. We're going to be underneath that horizontal asymptote. So this up here would be if a was greater than 0. Because a is less than 0, we're to be at the lower end. And because my base is greater than 1, we're going to move away from the asymptote rather than towards it. If my base was less than 1, we would move towards the asymptote. Because it's greater than 1, we're going to move away from the asymptote. So this graph is going to look like this. So that would be the graph of m of x. So if I wanted to write these end behaviors, how I would do so is on this one. You tell me. Go ahead and guess. This is called m. Let me name it m. Let's start with the x values. For the left end behavior, what are you thinking I should put for this x value? How far left does this graph travel?
Negative infinity.
Perfect. What about for the y values? What are the y values approaching?
Two.
It's a good guess. It's actually, I have it circled up there. It's the horizontal asymptote. It'll be approaching 1. It'll be approaching the d value. If you think of the equation in this way, if you think of it as, let's call it, I'll use a y. When I say the d value, what I'm referring to is if you had a times b to the power of x minus c plus d. The d value will be the horizontal asymptote. So that's what it approaches on the left. Now let's talk about the right end behavior. On the right, it looks like the graph is going down and to the right without bound, meaning there's nothing to stop it. It's going to go down and to the right forever. So to go down, you'd use negative infinity, and to travel to the right, you'd use positive infinity. So that would be our limit as we go down and to the right. Now again, like logarithms, exponentials have one value that's not an infinity. So polynomials will be full of infinities on their limits, the end behaviors, but for exponential and logarithms, each one of them had one value that was not an infinity. So in this logarithm, it was the x approaching 2 plus. And for this exponential, it's just the limit of m of x as it approaches 1. Now notice, with the y values, you don't have to do the plus or minus. You only do that if you're approaching like a vertical asymptote or a break in the domain. That's the only time it will do a plus or minus. So it'll only be the x values. Let me say this one more time. Only these x values could have a plus or minus. And that's only when you approach a break in the graph where it's no longer continuous that you would have that. But if the graph is continuous, you wouldn't worry about that. Now let me move this out of here. Not sure where my undo button is. Okay. Now I know that's a lot of information there fast. How are we doing so far? Y'all doing okay?
Yeah.
Okay. All right, so now let's get into what we've been learning about here in Unit 3. Let's talk about sinusoidal functions, which again, that word's a mouthful. So this is a sinusoidal function, sinusoidal, which just means it's either a sine or cosine wave that's been transformed. And so this graph, let me ask you this question. Where's the midline on this graph?
Negative
X plus
3.
2.
Yeah, it goes off the d value. So it's y equals negative 3. So right here, this is the midline. So what does it mean if it's a sine function? This graph needs to be shifted left too, but a sine function usually starts at the origin like that, or at the midline. Now this graph would technically be shifted over to the left just slightly because it has an x plus 2. So I need to shift everything over if I want to make it perfectly accurate like that. So I would, if I want to list a point here, that point right there would be shifted left 2 and down 3 at the midline. Okay, so if this is my sine function, this would not have any end behavior. No end behavior. That's because as you go, whoops, I'm not spelling that correctly. As you go to the left or right, what is happening to the graph? Here's my question for you. Let me write this out. If I were to ask, what's happening as you go to the left? Is the function going up? Is it going down? Or is it flat? That's usually the question I ask. But with the sine wave, what does it look like? Is it going left, down, up? Where is it going as we go to the left?
Negative infinity.
Well, if it weren't sine, I'd agree with you. That arrow would typically mean like that. But sine is a wave, so will it go down like that?
No,
No. What happens?
it just goes on forever.
It just continues to make waves after wave after wave. This would have no end behavior because the function oscillates. No end behavior since the function n oscillates. That's the word, oscillates. So this function n here, or the sinusoid, since it's going up and down, up and down, up and down, it has no end behavior because it's not doing anything inconsistent. It's sometimes rising, it's sometimes looking like it's falling, sometimes it's changing direction, but either way, it's never going one direction. Since that's the word is oscillates. Since it oscillates, there's no end behavior. Okay. So now we've gone through F examples. What is that? A, B, C, D, E, F. We've gone through 7 examples there, 6 examples. So with that, I want to let you try one on your own. What do you think is true of this end behavior? I'll give you a few seconds to think through what you would get for this end behavior. Oops. Okay, so now rational functions. So now, if we want to look at key features of rational functions, rational means it's a polynomial divided by another polynomial. I want you to recall a few things from the past. Number one is when you look at a rational, you want to cancel any opposite factors, meaning anything that's multiplying that and dividing. So in this case, we have 2 factors that could cancel. So what are the 2 identical factors that I could cancel out in this particular problem?
X minus 5.
That's right. So the canceled factors are going to be the x minus 5. Okay, I want you to recall that if it's a canceled factor, that creates what we call a hole. And that's going to be a hole at x equals 5. And that's because the inside lies. What you do is you solve that value. So you'd say x minus 5 equals 0, and so you'd add 5. So we're going to have a hole at 5. Now, if you have a factor in the denominator, a remaining factor in the denominator, remaining factor in the denominator, if you have that, which we do, I'm running out of room, that creates a vertical asymptote. So we do have a remaining factor in the denominator, and that factor is x plus 2. So if x plus 2 is our, if that's going to create our vertical asymptote, what you do is you set that equals 0, and so we'll have a vertical asymptote at x equals -2. All this is going to help us graph in just a moment. Finally, if you have any remaining factor in the numerator, does anybody remember what that is?
The zeros, no?
The zeros. Remaining factors, let me make that plural, in the numerator, run out of space, that becomes the zeros. So in this case, we have x minus 2, which means we will have a 0 at 2, 0. That's where we'll have the 0. Okay, so what does this mean for graphing? Well, I want to draw a quick graph. Here's my x, here's my y. What I could do is I know there's going to be a 0, 2 to the right. So 2 to the right, I'm going to have a 0. Oh, I forgot, I got to do one more thing at the hole in a second. I'm going to have an asymptote at -2. So at -2, I'm going to have a vertical asymptote like this. And I'm going to have a hole at x equals 5. We haven't solved where exactly at 5, though. What I would need to do is plug in 5 to the remaining equation. So my hole would be whatever is 3 times 5 minus 2. I'm typing into the rest of the equation over 5 plus 2. That's where my hole, the y value, that'll be the y value. So I'm going to simplify this here. In the numerator, I have 3 times 5 minus 2. What is 5 minus 2?
3.
3. And so 3 times 3 is
9.
9. So it'll be 9 divided by 5 plus 2 is
7.
7. So my hole is going to be 5, 9/7. So if I go over 5, 1, 2, 3, 4, 5, there's 5. I would have a hole at 9/7, wherever that is. Let's just put it right there. I'm going to have a hole at that spot. Now, how do I know what my end behavior is going to look like? Well, here's what you could do on your graph. When it's a rational function, what the graph would look like is the remaining pieces if you try to divide this. So I want to distribute the 3 through. If I this equation, I could simplify it. If I distribute that 3 through, I have 3x minus 6 divided by x plus 2. Well, if I just divided that equation, if I thought through trying to divide 3x minus 6 by x plus 2, I mean, we could do a synthetic division here. You could say x equals -2 and do a synthetic 3x minus 6. And we could really quickly get the equation. This would come down. You shouldn't have to write that x there. The 3 comes down. 3 times -2 is -6. -6 and -6 is -12. That's the remainder, if you remember this. And so my equation is y equals 3. This graph is going to look like the equation y equals 3. Have I done something wrong? Why am I doing here? I solve for x. Why should I? It shouldn't be just a flat line at y equals 3. Let me go to the graph real quick. See what I'm doing wrong here. This picture we had, what was it? Y equals 3. Whoops. 3 parentheses. Was it x minus 5? Okay. X minus 5. And x. So -2 or +2 in the numerator. Let's see here. -2. -2 in the numerator divided by x minus 5 and x plus 2. Okay, so as you can see, let me zoom this out here. What's happening to the graph is we do have that horizontal asymptote at 3, like I was doing with a synthetic. So here's 1, that's 9/7. So 2 would be higher than that. Here's 3. So we'd have this horizontal asymptote at y equals 3. That's what I got. And then I would just connect my dots. That's what I'm leaving off. I would start at this asymptote. I would go through the 0, through the hole, and on to the right this way. And for the other end of my equation, it was out here like this. And so that's what my graph would look like. Now for my end behavior though, what you would go off of is this. That right here, that value will help generate my end behavior, this horizontal asymptote. My end behavior will come from that. So the reason of doing that was that's going to tell us that this is limit 1 and this is limit 2. The end behavior is talking about the left and the right. As we go to the left, our graph approaches 3 as we go left without bound. And as we go to the right, this function also approaches 3. So that's what this graphic, that's how you'd put that together. Now, unfortunately, not every rational function is going to be given to us in factored form like that. Which on this one, again, I did a lot of extra there that you wouldn't have to do, but I was just kind of walking you through the key features. But on part B, let's do this again. Let's talk about, I'll go in this order. What are my vertical asymptotes? What are the holes? And what are our zeros? Let's do this first. Okay, check out the equation. What can I do to simplify this equation?
Cancel out the x minus 7.
That's right. So what does that become? A vertical asymptote or a hole?
Oh, home.
Or 0. That's right. So the canceled factor is x minus 7, which means we'll have a hole at x equals what value?
7.
Okay, so what I'm going to do is I'm going to plug in a 7 to the rest of the equation to find the y value. So it'd be 2 times 7 minus 3 times 7 plus 1 over 3 times 7 minus 5 times 7 plus 5. Let's simplify that. In the numerator, I have 7 minus 3, which is 4. So 2 times 4 is 8. Times another 8 is going to be 64. Divided by, in the denominator, it's 3 times 2 times 12. So 3 times 2 is 6. Times 12 is 72. And that could reduce to 32 over 36. And again, to 16 over 18. Again, to 8 over 9. 8 divided by 9 is what that can reduce to. So we have a hole at 7 comma 8 over 9. That's where our hole will be. Okay, what about vertical asymptotes? Where will we have vertical asymptotes?
And the denominator?
That's right. So what about x minus 5? Where would that asymptote be?
X plus 5. Oh,
Okay.
x equals 5.
Yep, and then the x plus 5 becomes x equals
Negative 5.
negative 5. So we have two asymptotes. That's x equals 5. There's x equals negative 5. We have a hole at 7 comma 8 ninths. So if that's 5, this is 6, 7, 8 ninths is somewhere over here. It'd be almost 1, so I probably should draw a little bit lower. Can't do it now. We'll leave it there. And what about zeros? Where does this function have zeros?
X equals 3 and x equals negative 1.
That's right. At 3 and negative 1. So at 3, 0, we have a 0 and negative 1, 0. As far as end behavior goes, this function, if you multiplied it all out, basically what we have in the numerator, if you distribute it out, is I'm just going to kind of write it this way, is you'd have y equals the leading term would be 2x squared divided by 3x squared, which can simplify to 2/3. So this will have 2/3 is a little bit below the hole. End behavior that's approaching right in here like that. So my guess what this function is, we'll graph it now. Going off the hole is I'm guessing this graph is going to come in like this, around that hole like so. And over here, it'll probably go like this, hit those two zeros. This is all just a guess, by the way. We'll check it out in a second. And then like that. That's going to be my guess of what this graph is going to look like. Just connecting points with asymptotes. Let's double check. So we have y equals 2. Oops. It was x minus 2. No, it wasn't. It was x plus, no, x minus 3. And then plus 1. X minus 3. X plus 1. And x minus 7. All that divided by 3 times x minus 7, x minus 5, x plus 5. X minus 7, x minus 5. Whoops, it is 8. And x plus 5. So, yep, it looks like we guessed correctly on the graph. And we should have that hole, if we zoomed in, right at 7. If I get to 7, yeah, there it is. It goes undefined there. We had the 0 at 3. We had another 0 at -1. Yep, and this horizontal asymptote is at the equation y equals 2/3. That was our, what did I do here? Let's try this again. Y equals 2/3. That's our horizontal asymptote that this graph approaches. Notice there is an intersection, which is okay. That is okay, but the graph, as you go to the right and as you go to the left, it approaches 2/3. So we can now fit in our limits here. And so the two limits on this particular problem, this particular rational, would be coming from this part of the graph and this part of the graph. So as I go to the left, this function approaches 2/3. And as I go to the right, whoops. And as I go to the right, the function also approaches 2/3. That's how you'd write the end behavior of those rational functions. Okay, now as we approach our finishing the end of our time here, what I'm going to do this time is I'm going to give you a rational function. These were rational. I don't think I wrote that in the last one. This is rational. And this previous problem was also rational. These were at the end of unit 1 is when we first discussed these. Okay, well, as we kind of wrap up here, I'm going to show you a rational if it's not in factored form. Now, if it's not in factored form, what you can do is you could still determine the end behavior by the horizontal asymptote. What you try to do is take the leading term and divide it by the leading term. Now, in this particular case, 4x cubed could not divide into 2x squared. So for that reason, the horizontal asymptote is going to be at 0. That's going to be our horizontal asymptote. You take your leading term divided by leading term, it's going to be 0, which means when we graph this graph is going to go left and right following the x-axis, as we'll see in a moment. But to find my key features, if I were going to do that, what I would have to do is get this into factored form. And so what I would need to do is factor the numerator. So the numerator here, I'd use factors of a times c divided by b. So 2 times -12. 2 times -12. What is 2 times -12?
-24.
That's right. They need to add up to be 5. So the factors of -24 that I can think of. 1 and -20, 1 plus or minus 1 times plus or minus 24. So 1 and 24, 2 and 12, 3 and 8, 4 and 6. I think that's all of them. 1 and 24, 2 and 12, 3 and 8, 4 and 6. Which one has a difference of 5?
8 and -3.
Very good. 8 and -3. 8 times -3 is -24. And 8 minus 3 is 5. Perfect. Okay, so we factored that. Now I'm going to be quicker here because this lesson is not about the factoring here. But when you factor it and you have an a value that's greater than 1, what you need to have is in your parentheses, one of these two parentheses needs to have a 2x. The other one's only going to have an x, which means one of these two numbers is going to simplify by a factor of 2. It's the 8. So in the parentheses that only has an x, it's kind of like that 2 has been simplified with the 2 that's dividing the 8. That needs to be x plus 4. That 8 becomes a positive 4, right there. Becomes just a 4. Now on the -3, because that can't be simplified, that's going to be 2x minus 3. Now in the denominator, there's a GCF. What do they both terms share in the denominator? What do they both have?
X.
They both have an x. So if I factor that out, what I'm now going to factor is 4x squared minus 9. And so on this one, I'm looking for factors in -36 that add up to 0.
6 and 6.
That's right. 6 and -6. Perfect. Again, because this has a factor, excuse me, it's 4x squared, the 80 term. I need to simplify this a term. And so how do I do that? What I would do is, since it's a factor of 4, a lot of times it might be, you might think of it as being a 4x and an x, but it can be simplified. This one's going to be different. Both 6 and -6 can be divided by 2. And 2 times 2 is 4. So what's going to happen is both of them are going to get simplified by a factor of 2. So this will be 2x plus 3 and 2x minus 3. So that is equal to 3. That's equal to -3. Since they both got divided by 2, both terms get the 4x. When you split the x squared, get both of those get divided by 2. And so that's going to be my factored form. So what does that mean? Well, it looks like I have a hole. I have a hole at 2x, or from the factor 2x minus 3. So 2x minus 3 is going to create the hole, which means x itself would equal +3 divided by 2. To find the y value, I would plug that into the equation once left over. So 3 halves is like 1.5. Let me just leave it as 3 halves. Okay, so I would have 3 halves plus 4. I guess I don't need the parentheses anymore, since there's nothing for that to multiply with. So 3 halves plus 4 over 3 halves times 2 times 3 halves plus 3. Now to simplify this, the 2's cancel with one another there. So I have 3 halves plus 4. 3 halves plus 4. 4 is the same thing as 8 halves, so this would become 11 halves in the numerator, because 4 is 8 halves, and so 3 halves plus 8 halves becomes 11 halves. And the denominator, the 3 plus 3 is 6. So I'm multiplying, it would be 3 times 6, which is 18, divided by 2, which is 9. So it's 11 halves divided by 9. 11 halves divided by 9, that's the same thing. 11 halves divided by 9 is the same thing as 11 divided by 2 divided by 9, which becomes 11 divided by 18. And so this has a hole at 3 halves, comma, 11 over 18. Now that was a lot of math there, which I don't necessarily want to get into today, but that's where that hole would be. So somewhere between 1 and 2, that's 3 halves, we'd have a hole at 11 over 18. So somewhere in there, we're gonna have a hole. Now we already said at 1, we're gonna have a horizontal asymptote. Let's go ahead and add that. That's y equals 1. We have a horizontal asymptote. And I have 2 vertical asymptotes. I have a vertical asymptote at x equals 0 and another one at negative 3 over 2. So x equals 0, I have a vertical asymptote and negative 3 over 2, which if that's negative 1, that's negative 2. It's going to go right in between there. That's x equals negative 3 over 2. Finally, we had a 0, which I haven't written on here. This graph has a 0. And the 0 occurs at negative 4. Three, 1, 2, 3, negative 4. We have a 0 there. So going off this graph, I'm assuming this graph is going to come through here like that, hit the 0, and approach this asymptote. And since I have a hole here, it's going to approach this way, which means I'm going to assume this graph's going to go up like that. Considering it doesn't have any zeros in between, I'm going to assume it looks like that, just connecting points. And so now I'll graph it. H of x being 2x squared plus 5x minus 12. I'm just going to type in y equals 2x squared plus 5x minus 12 all over 4x cubed minus 9x. So I was off in my estimation unless I typed in something wrong. Oh my goodness, I see what I did wrong. I said it approached 0 up top and then I graphed it at 1. That was a huge mistake. My asymptote right here wasn't supposed to be at y equals 1, it's supposed to be y equals 0. Goodness, goodness, goodness. Okay, that's where I threw all my graph off. So let me take these pieces out. Okay, let's try this again. We were supposed to have an asymptote at y equals 0, not 1. So y equals 0, here's the asymptote. And for that reason, since this is my hole right there, I would come from this asymptote and approach this one like that. And so over here, it comes up this way. This one's tricky, it goes underneath and comes back. And then this middle piece like that. That's actually how it looked. Let me make sure I have that right. Yeah. And so this should have a hole at whatever. There it is right there. -1 or positive 1.5 or 3/2. That's where our hole was. Okay, now that I have the graph right, let's do our end behavior. So what is this graph? Let's call this limit 2. This one's going to be limit 1. So what's happening on this graph is if you go to the left, limit of h of x, it's approaching 0 as you go left. And as you go right, it does the same thing. Oh, this is an f, this is h. It approaches 0 as you go to the right. And so those limits we come up with by doing the division of the leading terms. That's where you can get the limits, or the end behaviors, I should say, of a rational function. So after all that, here we are wrapping up out of time. I have one DOL left. If you want to work through this one, you can just send me the end behavior, because that's what the majority of today was about. If you want to send me the end behavior, I'll give you credit for being with me.